All right, welcome back. Um, so I wanted to spend some time talking about the finite square wall today, although I received a couple of requests to spend a little bit more time uh, on the beginning of the Schrodinger equation for you again. Um, who knew that people were actually watching these videos? Um, I'm glad. So I'll try to expand a little bit on the Schrodinger equation for you from our last lecture also. Um, but first, last week we had spoken of the Bohr atom for hydrogen, um, and you'll recall uh, that he had these stationary states, which when the electron was in one of those stationary states, it needn't uh, emit electromagnetic radiation. Um, but there wasn't uh, justification for why that should be so. And so today, just really quickly, I wanted to talk about Louis de Broglie, um, French physicist. He was of uh, uh, minor nobility. He and his older brother. Originally, Louis uh, uh, studied humanities and aimed for a career as a diplomat, but his older brother chose to be a physicist, and De Broglie, Louis, followed in his footsteps. So, uh, in graduate school, he had what was a remarkable insight. Um, he was aware of this Bohr atom, um, and he was also aware of Einstein's photoelectric effect. And recall that Einstein told us uh, that light was simultaneously a wave and a particle, and de Broglie uh, extended this to the electron in the atom. So Einstein said that the the photon could be, or that light could be simultaneously exhibiting particle and wave properties, and it just depended on how you that it was simultaneously both a particle and a wave, and depending on how you tested it, um, it would exhibit uh, one form or the other. De Broglie uh, thought of that perhaps everything was both simultaneously a wave and a particle, and so he imagined a matter wave where this electron orbits, um, and he imagined constructive interference and destructive interference, and and the way that he envisioned this is the wave properties of the electron were such that uh, if the circumference of this orbit was an integer multiple of its wavelength, then the orbit was stable. If not, then you would have destructive interference, and uh, and that wouldn't be a steady state. So de Broglie assumed that these steady states came about uh, from uh, in other words, this quantization of allowed orbits came about uh, from insisting upon constructive interference of uh, of the matter wave of the electron. And it's actually that's his PhD thesis. Um, it's actually Einstein who saw this and uh, was I was very impressed by this, and that's one of the ways in which Louis de Broglie became a famous physicist. actually winning the Nobel Prize in 1929. Um, it's a really interesting story, and I recommend that I that you that you read it. You can, find it in many online resources. As it turns out, it's not entirely correct. So um, so we don't really think of the electron kind of sweeping out wave-like motion. That's not the modern interpretation of quantum mechanics. But it really did influence a lot of the early quantum mechanical theories, and and set about a whole bunch of research uh, that is eventually leading us to our more modern interpretation of quantum mechanics. So I'll leave you uh, to look that up on your own. But uh, since since we got questions about the Schrodinger equation and what the difference between the time dependent and the time independent Schrodinger equation were, I thought that I would try and flesh that out a little bit more before we advance further. So first, I'll remind you of the one-dimensional time-dependent Schrodinger equation, and it goes as minus h bar squared over 2m times the second partial derivative of psi with respect to x plus this potential term times psi is equal to I h bar times the first partial of psi with respect to t, and h bar is just h over 2 pi, so 6.626 times 10 to the minus 34 joule seconds divided by 2 pi is about 1.054573 times 10 to the minus 34 joule seconds. I want to talk again about this Born statistical interpretation of the wave function, Max Born. Um, so it is quite simply put that unlike kind of this idea of the electron kind of moving about like in a wave-like pattern, instead the wave function isn't describing the physical motion of the electron. Instead, uh, the wave function, or at least the square thereof, is related to the probability of finding the particle at some point x at some time t. And if we want to find the likelihood that the particle is in some range x to x plus dx at some time t, well, that's just going to be uh, psi star psi squared times dx. And so to put a little pictogram to this, if this oddly drawn curve is psi squared, then then what we see here is that uh, the particle is very likely to be found near A, right? It has a very high amplitude here, psi squared. It is not likely to be found at B, right? Um, it has basically a zero chance of finding it at point B. Um, this shaded region here, dx, or the shaded region between dx and bounded by the horizontal axis and psi squared, the shaded region represents uh, the probability of finding the particle in this range dx. So that's this Born statistical interpretation of the wave function. It's not describing the physical motion of the particle. It's describing the likelihood of finding the particle at some region of space at some time. Now, I'm going to digress just a moment and talk about indeterminacy. And so if we conduct some experiment and we find the particle, this horizontal axis is x, at point C, so the particle is at x equals c, you might ask yourself, where was the particle before we observed it to be at point C? And this was quite the argument in the first half of the 20th century. Um, and kind of the rough breakdown of uh, the three kind of answers to that question could be thought of as realist, orthodox, and agnostic. So the realist interpretation was, where was it before it was at sea? Well, it was already at sea, right? D'Espagna. Uh, this isn't a direct quote, but um, the gist of it is that the particle wasn't lost, right? It just wasn't known. Its location just wasn't known to the experiment, right? So until you looked, you didn't know it was there, but that doesn't mean it was there before you looked. That's kind of this first interpretation. The second interpretation is the particle wasn't anywhere. The experiment itself collapsed this wave function, right? It had some probability of being at all of these locations. It wasn't until you conducted the experiment that it collapsed the wave function and, at least momentarily, gave you a spike in the wave function. And then if you allow this to evolve over time, it will broaden again. It will go from being something like that uh, to kind of a broader structure again. Um, that's that's this Copenhagen interpretation. Um, it's the experiment itself that actually collapses the wave function and allows you to say that the particle is there. Um, we're going to talk about this some more. Um, the kind of uh, pop culture uh, cliched Schrodinger's cat. You might have heard of the Schrodinger's cat experiment. It's a thought experiment. It's not real, or it didn't really get conducted. It's in your head. Um, is kind of the battle between these two ideas, and it's kind of an extreme example, an absurdist example of what might happen if you took this idea too far. Um, there's a third interpretation, which is we don't know whether it's one or two. We don't know whether the particle was at sea before we started looking for it, and we don't know if the particle wasn't at sea before, right? That it was, that it was undefined before we started looking for it. And so this third approach is you can't distinguish between either of these two cases, and so why are we having this fight? Except that in 1964, Bell conducted a set of experiments that showed it actually does matter. That that three is not fair. That it's not just uh, an exercise that has no real consequence or relevance. It actually does have fundamental meaning, and so it does matter. So it's not three, and even crazier, the the results of these experiments seem consistent with two. So that again, before you started uh, the experiment, there was some probability of finding the particle at any of these locations, and it was the carrying out of the experiment that localized the wave function and allowed you to observe the particle at point C. So again, we will come back to this because it's neato. Um, but I also want to describe this idea of probability density, which we looked at back in our discussion of statistical mechanics when we were uh, talking about thermodynamics oh so long ago, right? And we can say that the probability density rho of x times d of x is this probability uh, of observing the particle between x and x plus dx. And if we want to know the the probability then of finding it between a and b, between x equals a and x equals b, then we just take the integral from a to b of rho of x dx. But this gives us this normalization criterion, right? The particle is somewhere, and so there has to be 100% this unity probability of finding the particle between x equals minus infinity and x equals plus infinity. And so 1 needs to equal the integral from minus infinity to infinity of rho of x dx. And remember our expectation value, the expectation of x is just from minus infinity to infinity of x times rho of x dx, right? We just took this and multiplied both sides by x effectively. We could do this for any function of x. In fact, the expectation value of f of x is just the integral from minus infinity to infinity of f of x times rho of x dx. And we can also look at uh, uh, this idea of what we're going to call sigma squared is just, and that should be sigma x squared, but is equal to the expectation value of delta x squared, which is just the expectation value of x squared minus the expectation value of x quantity squared. And we'll come back to that. But this does tell us that um, that we can say that the integral from minus infinity to infinity of psi star psi dx is equal to 1. Psi star psi is just the the complex squaring of psi. So if you guys haven't ever taken complex conjugates in one of your math classes, um, I would pause the video here and Google complex conjugate. So remember, our time-dependent Schrodinger equation is here, right? This is usually way too crazy for us to solve, and very much so if we're talking about uh, a, a lower division physics course, right? A non majors physics course. Um, and so let's help ourselves out a little. We're not going to look at every possible solution to this equation. Instead, let's restrict ourselves to a subset of possible problems. And so let's look at the subset where the potential term, the potential is independent of time. In this case, we can take a separation of variables approach, which you probably have run across in your math courses by now. If that's the case, we can say that uh, psi of x and t is equal to psi of x times f of t, so that psi of x does not depend on time and f of t does not depend on position. Hooray? So basically, this function, which itself depends on both position and time, is actually just the multiplication of a function that is purely dependent on position multiplied by a function that is purely dependent on time. And this is actually going to be very powerful for us because it will allow us to get to the time-independent Schrodinger equation. Note that if this is our statement, we can take the derivative of this with respect to time, and what we get is that d psi, so partial psi with respect to t is just equal to psi times df dt, right? Hopefully you can convince yourself that if this is the statement and you take the derivative of this with respect to time, you just get this. The second derivative of this equation with respect to x is just this, right? Again, f doesn't have an x dependence, and so it's just d squared psi dx squared times f. Yay? If you have to, pause the video here and convince yourself that you can go from this top line to this equation and from this top line to the second equation. So from here, I'll point us back to our time-dependent Schrodinger equation, where we have IH bar times d psi dt, but we just solved for what we meant by d psi dt for this special case, right? And so I can replace this derivative with this. And so the right side of this equation, which, because I'm trying to make this hard, obviously, harder than it needed to be, I apologize. The right side of this equation just becomes IH bar times psi times df dt, right? So all I did is subbed psi times df dt in for this, okay? The left side of this time-dependent Schrodinger equation, which again, because I don't know why I did this, I put it on the right side over here. If I replace this d squared psi dx squared with this second equation, I can say that d psi squared dx squared is just d squared psi dx squared times f. And so, um, so we wind up with, and I can sub in for psi of x and t, I can just sub in psi times f, right? The left side of this equation, which again, I apologize, I put on the right side over here, just becomes minus h bar squared over 2m times d squared psi dx squared times f plus v psi f. So convince yourself that using these as your substitution values, if you plug those in to the time-dependent Schrodinger equation, that you get this statement, which is still time-dependent, right? We haven't changed anything, just written it in a weird way. Now I want to divide both sides of this equation by psi times f. And if we do that, we get on the left side IH bar times 1 over f times df dt. And on the right side, we get minus h bar squared over 2m times 1 over psi times d squared psi dx squared plus v. Yay? You can divide both sides of this equation by psi f and get this equation, yeah? Well, the interesting thing here is now the left side of this equation is really just a function of time. We've gotten rid of any x dependence on the left side, and on the right side, we've gotten rid of any time dependence. It's really just a function of x now. And we could scale this up to 3 dimensions if we wanted to. It's just, I think this is probably challenging enough in 1 dimension. So now we have two sides of the equation that are uh, one side is only a function of time, the other side is only a function of x. And so the only way that can be possibly true, that they're still equal to each other, right? I could go to a different x position and still have it equal to this same thing at the same time on the left side. The only way that the two sides of this equation can equal each other then, because I could possibly vary the position or I could possibly vary the time, uh, and it still has to uh, equal the other side, even if I made no change to the other side of the equation, right? The only way that can be true is that both sides have to equal a constant value, and this constant value is going to wind up being e. Hooray? See if you can convince yourself of this. Um, if you have an equation that says I that 3t squared on the left is equal to 4x on the right, well, the only way that can be true is if 3t squared is itself a constant, and on the right, 4x itself is a constant value. That's all we're arguing. So there's some constraint here that they both, in order for them to equal each other, they both must equal a constant. But now we have this statement that IH bar times, right, the left side of this equation, IH bar times 1 over f times df dt is equal to E. Well, we could say then that solve for df dt. df dt is just equal to minus IE over h bar times f. What kind of function have we seen where the first derivative is just some constant times the original function? Well, we've seen that a lot. Those are exponentials, right? So our trial solution is that f of t is just equal to e to the minus iet over h bar. Note that if you took the first derivative with respect to time of this, you would get minus ie over h bar times e to the minus iet over h bar. Um, and so, um, so we now have our description for what we mean by the time dependence of psi, right? Psi of x and t is just psi of x times f of t, but we're now saying that f of t is just e to the minus iet over h bar. Right about now, you might be asking yourself um, why people asked for me to go over this in greater depth, but hopefully you're finding some beauty or joy in this. So the other statement we have is the right side of this equation, right? The right side of this equation also needs to equal a constant, same constant. So we have that minus h bar squared over 2m times 1 over psi times d squared psi plus, d squared psi over dx squared plus v is equal to e. Um, well, this is a little bit easier. We're just going to multiply both sides of this equation by psi, and we get minus h bar squared over 2m times d squared psi dx squared plus v psi is equal to e psi. You might recognize that. That is what we described as our time-independent Schrodinger equation from last time, right? This isn't a formal proof, right? We started by assuming our time-dependent Schrodinger equation. But from the time-dependent Schrodinger equation, we can get to the time-independent Schrodinger equation by assuming separation of variables. So ultimately, psi of x and t then is just psi of x times e to the minus iet over h bar. Hooray. Note then that if we have uh, psi star psi, which is just our psi squared, right? Um, psi star is just the complex conjugate of psi, and so it's how you deal with squaring things that might have complex components. Um, and so if we take psi star psi, well, if psi is just psi x e to the minus I e t over h bar squared, well, the complex conjugate of this would just be psi star, the minus I becomes plus I, so psi star e to the I e t over h bar. Hopefully you looked up complex conjugates so that it gave you a little refresher. Um, but the complex conjugate of psi is just going to be psi star e to the I e t over h bar times psi itself is psi e to the minus I e t over h bar. If I take these things and multiply them together, e to the I e t over h bar times e to the minus I e t over h bar, that's just 1. And what we're left with is psi star psi, which we could write as just psi of x squared. Hooray! We're also going to apply boundary conditions. So um, because uh, psi is related to the likelihood of finding the particle, psi and d psi dx both need to be continuous at point by point unless the potential locally tends towards infinity. Um, in fact, does not tend towards infinity. I'm not entirely sure how I screwed that up, but um, if we approach point x equals a from the positive side, from the plus infinity side, and we approach x equals a from the minus infinity side, well, psi of a, whichever direction you approached from, needs to approach a constant value or an assumed value. And so what that tells me is that psi of a from the plus direction needs to equal psi of a from the minus direction. You've probably done continuity tests like that in your calculus courses. Additionally, um, the the slope of psi with respect to x needs to be continuous whether we approach from the plus side or the minus side, um, the positive infinity side or the negative infinity side, um, at x equals to a, right? And so long as the local potential doesn't approach infinity, then d psi dx is also continuous. You may recall that in our infinite square well example, the local potential did approach infinity here. So remember that we didn't insist on continuity of d psi dx. There's some games that we played, but ultimately, go back to the last lecture if you're having trouble remembering how we got here, but psi of x is equal to 0 for in this region 1 where x is less than 0. It's equal to 0 if x is greater than L, region 3, and in between it's equal to the square root of 2 over L times quantity sine of n pi x over L end quantity between 0 and L, which is region 2. And this led to quantized energy levels of pi squared h bar squared n squared over 2ml squared. Note that as L gets smaller, the quantized energy levels get bigger. Hooray. Hopefully that's hopefully you watched that lecture enough that it made sense. Um, Today's piece is more challenging. We started with the infinite square wall because it solves very nicely, and I think you probably um, had had uh, warmer feelings for the infinite square wall than you're going to have for the finite square wall. But again, this is really and truly mind-blowing and beautiful, and I hope that I can do it justice. So this time the potential doesn't go all the way up to infinity. It only goes up to a height of v naught. The approach I'm going to do is I'm just going to shift the energy floor down, and so I'm going to say that x greater than a. Note that this time, rather than going from 0 to L, I'm adding a little bit of symmetry, and I'm going from minus a to a. You could still do this from minus L over 2 to L over 2 and still have it be L wide. I just don't want to get these two things confused, and so I've drawn a little bit of separation here by just changing the spatial coordinates. But for x greater than a, I'm setting the potential to 0, and x less than minus a, I'm also setting the potential equal to 0. But in between, I'm actually setting the potential to minus v naught. And here, just to be really, really pedantic, um, I've I, I've said minus the absolute value of v naught, just so that we're clear that when I say v naught, I mean a positive value. So minus v naught, minus the absolute value of v naught is the depth of this finite square wall, right? This was an infinite square wall because the walls went all the way up to infinity. This is a finite square wall because the walls are only v naught tall. Hooray! We could look at a particle um, approaching this well um, and scattering off of it. That's definitely one of our upcoming lectures. But today I want to look at bound states. So what does it mean to be bound? In this case, well, it means that the energy is less than 0, right? Think of our study of the hydrogen atom thus far, right? We haven't finished the hydrogen atom, but we talked about the electron, uh, the energy of the system is being negative, right? In the ground state, it's about minus 13.6 electron volts. Um, uh, the minus just tells us that the system is bound together. The nucleus and the electron are bound together. Here, the E being less than 0 just implies that it's also bound, right? The wall is at least classically taller than um, I than the amount of energy that this particle has. You should also note um, that it's not possible for the energy to be less than minus v naught. And so really I could even go further and say that the energy is less than 0, which is up here, but it's greater than minus v naught. Hooray? Okay, let's look at different regions again. So again, we'll go with region 1, region 2, and region 3. Um, in region 1, which is x less than minus a, we have, well, coming back to our time-independent Schrodinger equation, right? What's V? Well, V is 0 out here. And so if V is 0, this term goes away, and we just get that minus h bar squared over 2m times d squared psi dx squared is equal to E psi, because this term is 0, right? And so we can rewrite the Schrodinger equation as just that. Minus h bar squared over 2m times d squared psi dx squared is equal to E psi. I could multiply both sides by minus 2m and divide both sides by h bar squared, and I would get something in this form. D squared psi dx squared is equal to kappa squared psi, where kappa is just going to be the square root of minus 2me over h bar squared, or I can bring the h bar out of the square root and get the square root of 2m minus 2me in the numerator divided by the denominator not under the square root of just h bar. Remember that e is less than 0, right? And so minus 2me is actually a positive number. The mass is always positive. And so minus 2me is minus 2 times a positive mass times a negative energy. Minus times minus is positive, and so this thing is uh, the square root of a positive number divided by h bar is kappa. Yay? Well, what function, if I take the second derivative, yields the original function times a constant squared? Well, you've seen these before. The solutions of these types of equations are a e to the minus kappa x plus b e to the kappa x. Hooray? This is the mathematical solution. The physics is important here, though, because we're looking at this in region 1. In region 1, we have that x is less than minus a, meaning that x is a negative number. We have to be careful here because this should be true for any value of x less than minus a. And what happens as we start to head out towards minus infinity? Well, this first term, e to the minus positive value, positive real value, times minus infinity is e to the minus minus infinity, e to the infinity is infinite, right? This term becomes infinitely large as we approach minus infinity, as x approaches minus infinity. But that can't possibly be true, because remember that the probability of finding this thing is psi star psi, is the square of this function, right? If one of the terms approached infinity, then it would imply that you had an infinite likelihood of finding the particle, which isn't possible, right? It's not normalizable. It has to have a 100% probability of finding it somewhere, no more, no less. It can't have an infinite probability of finding it, right? It's limited to have no more than 100% or 1 if you're doing it fractionally. The second term doesn't have that problem, right? As x approaches minus infinity, kappa is a positive term, right? We just decided that up here. And so this would be e to the minus infinity as we approach infinity times b. But e to the minus infinity is 0. And so that's not a problem for us. And so what we're going to do is we are going to throw out this first term. We're going to say a is equal to 0. And so in that case, psi in this first region, in region 1, is just going to look like be to the kappa x. In region 2, well, we're not quite as lucky this time, right? This time in our Schrodinger equation, time-independent Schrodinger equation, v isn't equal to 0, so we do have to account for it. And so our Schrodinger equation looks like minus h bar squared over 2m times d squared psi dx squared minus v naught psi is equal to e times psi. We could play that same silly game that we played up here, where we just solve for d squared psi dx squared. And we can do that by saying that d squared psi dx squared is just equal to minus L squared psi, where L is just going to be defined as the square root of quantity 2m times quantity E plus V naught and quantity, all divided by h bar, right? So convince yourself that you can go from this statement to this statement with the knowledge that L is that. Pause the video here and just double check. Humor me, please. Here, again, we're insisting that E is less than 0, but again, E has to be above the floor, and so we could say that minus V naught is less than E is less than 0. And so note that that also insists that L is going to be positive and real, right? Because the absolute value of V naught is going to be more than E, right? One way of thinking about that is if this is 0 and E is minus 8, then minus the absolute value of V naught could be something like minus 10, right? But that tells me that V naught has to be 10 because E has to be greater than the negative of the absolute value of V naught, right? Hopefully that makes sense, since E is pinned between 0 and the negative value of the absolute value of V naught. Well, again, going to our silly analogy, if E is minus 8 and minus absolute value of V naught is minus 10, that says that V naught has to be 10, or at least absolute value of V naught has to be 10. Minus 8 plus 10 is 2, right? Is positive. 2 is positive, m is positive, so everything under the square root is positive. So this is not complex, it's real, right? Hooray. And so what we have is d squared psi dx squared is equal to minus L squared psi. Then what functions have we seen where the second derivative yields the original function times a negative constant squared, or a constant squared and then negated? Well, those are sines and cosines, right? In fact, we did these at our last lecture. So we have psi of x is equal to c sine Lx plus d cos Lx. This time, I don't yet have enough information to do anything with the c or the d. But we have one last region, region 3. In region 3, it's just like region 1 again, right? Because v goes back to 0. And so our time-independent Schrodinger equation looks like minus h bar squared over 2m d squared psi dx squared is equal to e psi, right? The v term went away because v is 0. And so again, this looks like d squared psi dx squared is equal to kappa squared psi, right? That's this. Kappa is again equal to minus 2 me over h bar. Remember, e is still negative, so uh, so that implies that negative times negative is positive. This is also real and positive, right? And so again, the solutions to that are similar to what we had up here. I'm going to change the coefficients just so that we can distinguish, but psi of x is equal to f e to the minus kappa x plus g e to the kappa x. This time is, since we're in region 3, that's x greater than a, we have to worry about what's going to happen as we approach positive infinity. And this time, the second term is going to blow up as become infinitely large, right? As we approach positive, as x approaches positive infinity. And so combat that, we're going to let g go to 0 so that in region 3, psi looks like fe to the kappa x. Yay, so in region 1, we had we had b e to the kappa x in, I was wondering why that looked so weird. We have fe to the minus kappa x. Sorry about that. Yay. So in region 1, just to fix this, we have psi is be to the kappa x. In region 2, we have that psi is equal to c sine lx plus d cos lx. In region 3, we have that psi is equal to fe to the minus kappa x. I didn't bring the kappa or the minus down, right? Yay. Okay, if you're still with me, congratulations. Let's impose continuity. So let's impose continuity of psi and d psi dx at x is equal to plus and minus a, right? At these two boundaries between region 1 and 2 and between region 2 and 3. Um, the other trick here is a neat little math trick that you probably learned uh, in one of your differential equations courses, but since the potential here is even, by even I mean that v of minus x is equal to v of plus x. It's symmetric about x equals 0. Since the potential function is even, meaning symmetric about the origin, the solutions for psi either need to be purely even or purely odd. It can be either, but that really limits the possibilities that we have to explore. And what that tells us is that psi of minus x is either equal to psi of x, or psi of minus x is equal to minus psi of x. Again, just to put numbers to this, psi of minus 10 is either equal to psi of 10, or psi of minus 10 is equal to minus psi of 10. Just in case you're wondering, cosine is an even function, sine is an odd function, and so we can break our solutions, right, into purely even or purely odd. And so um, so I'm going to just explore the even solutions today. Note that as an exercise, you could go through and solve the odd functions also. Um, if you want to do that and you want to check how it turns out, check with me, and I'm happy to go through it with you. Either check your work, or we could just work on it together in an office hour. Let me know. But in our even attempt, we have f e to the minus kappa x for x greater than a between 0 and a, we have d cosine Lx. How did I throw away the c sine Lx? Well, remember, this is our even solution attempt. And so we're only keeping the even function, and we're going to throw out the odd function. And so that should give you a hint as to how we would approach this if if we were making the odd attempt. And for x less than 0, we're just going to say that psi of x is equal to psi of minus x. Hooray. Um, so hopefully that's okay. In other words, this thing perfectly mirrors about the origin. In our odd attempt, whatever you had from 0 to plus infinity, you have the negative values from 0 to minus infinity. That would be the difference in the odd attempt. Hooray! So it would be instead of psi of x is equal to psi of minus x, you would say psi of x is equal to minus psi of minus x. Hopefully that's all right. Okay, so let's insist upon continuity of psi at a. And so we have these two things that need to equal each other at x equals to a. And so we have f e to the minus kappa a has to equal d cosine L of a, and I'm going to call that equation 1. We also have continuity of d psi dx, and we can say that, well, if we take the first derivative of this with respect to x, we get minus kappa f e to the minus kappa a at x equals to a, right? So don't plug in the a before you take the derivative, plug in the a after you take the derivative. And then if we take the derivative of this guy with respect to x, we get minus dl sine of Lx. Plugging in x equals to a, we have minus ld sine of La. And so we have that ultimately minus kappa fe to the minus kappa a is equal to minus ld sine of La. And I'm going to call that equation 2. Hooray! Now we're going to take our equation 2 and divide it by equation 1. Why? Because I've already seen how this story ends before, but 2, oftentimes where I have equations like this where I can take sine and divide by cosine and turn it into a tangent, I like to see what happens if we do that. And so if I take equation 2, divide by equation 1, the right side of this just becomes minus L tan La. If I take the equation 2 and divide by equation 1 left sides, we get minus kappa. And so we can say that minus kappa is equal to minus L tan of La. The minus signs cancel. We get that kappa is equal to L times tangent of La. I'm calling that equation 3. I'm losing my voice, so um, let's see if we can save a few syllables, and I'm just going to define z to equal L times A. So everywhere that we have in LA, I'm just going to start calling it a z. I'm also going to insist that I'm going to define z naught as a over h bar times the square root of 2m v naught. We also have then that L is going to be 2m times quantity e plus v naught, all of that under the radical. And then, of course, we have to divide by h bar, right? We actually had already stated this up here. L is 2m e plus v naught over h bar. Yay? That's just this. And we also have that kappa is the square root of minus 2me over h bar. Remember that we had that way up here. How is any of this any better? Well, note that if I take kappa squared plus L squared, um, the 2me in the numerator is going to cancel, and what I'm left with is kappa squared plus L squared is 2m v naught over h bar squared, right? So I'll ask that you pause the video after this, square L, square kappa, add kappa squared and L squared together, and convince yourself that you get this. So pause the video here, see if that's true. Okay. Note that that is also the same as z naught squared over a squared. So if you pause the video here, or maybe you can just see this, if you square z naught, you'll have a squared times 2mv naught over h bar squared, and if you divide that by a squared, you'll have 2mv naught over h bar squared. So what we have is that kappa squared plus L squared is equal to z naught squared over a squared. We could take this new equation and say that if I multiply both sides by a squared, kappa squared a squared plus L squared a squared is equal to z naught squared. And so I could solve for kappa a squared as kappa a squared is just z naught squared minus L squared a squared. But we just said that z is equal to LA, and so we could write this as kappa squared a squared is equal to z naught squared minus z squared. So convince yourself that you can go from kappa squared plus L squared is equal to z naught squared over a squared, multiply both sides by a squared to get kappa squared a squared plus L squared a squared is equal to z naught squared, and then subtract over the L squared a squared term to get that kappa squared a squared is equal to z naught squared minus L squared a squared, but L squared a squared is z squared, and so this is really just kappa squared a squared is equal to z naught squared minus z squared. Hopefully you're taking notes and working along on paper, because otherwise this is going to be tough to follow. Note then that we can square root both sides to get that kappa a is just equal to the square root of z naught squared minus z squared. Yay? Hopefully that's not terrible. Look at our equation 3. Equation 3 looks a lot like kappa a. All I need to do is multiply both sides by a. And if I take equation 3 and I multiply by a, I get that kappa a on the left is equal to LA tan LA on the right. But now I have two equations both equal to kappa a. And so we can say that z naught squared minus z squared under the square root is equal to, well, LA is z, right? So it's just equal to z tan of z, right? This is interesting. The square root of quantity z naught squared minus z squared end quantity is equal to z tan z. That's gotta be close to something, right? The issue here is that this is a transcendental equation. And so um, the definition of transcendental equation is if you give me an explicit solution, I will give you uh, 1 point of extra credit. Um, so use your time judiciously. Um, it doesn't have an explicit solution. You can solve this computationally, you can solve this graphically, you can solve this by trial and error, and ultimately what you'll get is you can get an answer that satisfies as many decimals as you want, but you can't get an explicit solved answer. You couldn't solve this for z for me if you wanted to. Although if you do, I'll give you 1 point of extra credit. Um, one way of, so if I divide both sides by z, I can get to tangent of z is equal to the square root of z naught over z squared minus 1. So convince yourself that you can start out with our equations 1, 2, and 3, use these as our definitional statements, and convince yourself that you can ultimately work all the way to here. Tan z is equal to the square root of z naught over z squared minus 1. So again, this is a transcendental equation. And so what are we going to do? Well, we're going to graph it. We're going to graph both sides, right? So I believe that this one's green. I've graphed tangent of z. I've only graphed the parts that are above the axis, right? So this really also folds under the axis. But in green, we have tangent of z, and in blue, we have z naught over z squared minus 1 all under the radical, right? So that's this guy. So the solutions are everywhere. The solutions are everywhere where this intersects, right? So we have a solution here. We have a solution here. And we have a solution here in this bad pictogram. And then note that at some point, as z increases enough compared to z naught, z naught over z is equal to 1, at which point this just terminates, right? Because tan of because the term on the right, this z naught over z squared minus 1 under the radical, will go to 0. And if you increase z any more than that, then z naught over z squared is less than 1, and so this becomes irrational, right? Or complex. Hooray! We're happy with that. So I want to look at a couple of different cases. First, a wide, deep well. In this case, we're somewhat fortunate because a wide, deep well implies that z naught is huge, right? So coming back to our original picture, I had to scroll quite a ways up there, huh? That's a long lecture. Z naught being huge means that this well is wide and deep, right? So if the well is wide and deep, z naught is huge, but that also means that uh, that this becomes uh, effectively uh, effectively what we have is that this term on the right, if z naught is huge, z naught over z is basically still z naught, still huge. Squared is still huge. -1 is still huge. Square rooted is still huge, right? So the term on the right just approaches effectively infinity, right? If z naught is giant. So tangent of z tangent of z is equal to infinity. Where is that true? Well, that'll be true when z is n odd pi times pi over 2, right? It'll be uh, at pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. Um, so these, remember, are our solutions at even attempts, right? We would, to get a full set, we also have to go back and look at uh, the the odd solution case for a z not big. But what we're seeing here is that we get intersections here that will occur at the asymptotes. Yay? We could also think of a shallow narrow well. What I've drawn here is actually a case in between z naught huge and z naught small. So a shallow narrow well, if a wide deep well is z naught huge, a shallow narrow well must be z naught small. And so as z naught gets smaller and smaller and smaller, note that this curve starts to truncate sooner and sooner and sooner, right? But the thing that I want to point out is that there is always a crossing, right? There's always going to be one solution, no matter how small z naught gets. There will be fewer and fewer bound states, but there is always at least one bound state. That's the thing that I want to point out. That as soon as you had any dip here at all, there is at least one bound state. Yay? That is definitely different than quantum physics, a difference in quantum physics from classical physics. That says that, the tiniest little dip here means that there's always going to be at least one bound state. Um, we'll also look at scattering potentials in our coming lectures, but always at least one bound state. That's why I chose the even solution, because you don't get this result from the odd solutions. Um, all right. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow.